Hi, this is Miss Rosita. We're doing 3.3 Rules for Differentiation again. So this is our second video on 3.3. I'll include some more interesting problems than last time. Okay, let's get started. So for the first one I put, don't be afraid of rational exponents. When you're looking at the equation and the exponent is a 1/3, you could still use power rule. It doesn't have to be an integer. This one over here has a square root of x cubed. I could rewrite that as x to the 3/2 and once again use power rule. So with the power rule, I take this one, 1/3 comes down, x subtract 1 from the exponent. I get negative 2/3. And for the other term, keeping in mind it's x to the 3/2, so power rule, the 3/2 comes down, x, and then subtract 1 from 3/2, I get 1/2. And that's basically my answer. Over here on this one, since I have a square root of x on the bottom, I can, before I take the derivative, rewrite it as x to the negative 1/2. Again, the 3/4 is just the coefficient that stays out in front. So the 3/4 is out there. I do power rule. Negative 1/2 times the 3/4 is negative 3/8. X to the, and then I subtract 1. So negative 1/2 minus 1, negative 3/2. And then I went ahead and just tried to make it look like it did initially by putting it back into the denominator and using the root that it was originally written with. This last step here, just getting kind of fancy here, if you want to pull out the x squared out of the root, it would come out as an absolute value of x. Kind of a detail. Okay, you might also run into this one where it says solve the equation for dx of y equals 0. Again, this notation, I don't see it too much in our book. It's on your worksheet you're going to have tomorrow in class. But this just stands for derivative. It's another notation for it. So we're supposed to solve the equation where the derivative is 0. So here's my function. It's a quotient, so I'm going to do quotient rule. And once I figure out what the derivative is, I have to remember to set it equal to 0 and then solve it as you would any other problem. So with the quotient rule, we start with the bottom part, x plus 1, multiply by the derivative of the top. So term by term, we have 2x plus 2. Derivative of a constant here is 0. So just 2x plus 2. Minus the top equation times the derivative of the bottom. So the bottom's equation derivative of x is just 1. And the derivative of 1, since it's a constant, is 0. All over the bottom squared. So I multiplied out the whole numerator and tried to clean it up a bit, and eventually I got to here. Remember, you can multiply through by the denominator, it really goes away. So it's just numerator equals 0. I factored it and I got my answers. Okay, second derivative. Well, there's notation for second derivative as well. You can see them at the top here. These are all different ways to say second derivative. A second derivative is really just you take the derivative, and then when you get your answer, you take the derivative again of your answer. So second derivative, do it twice. So for my example here, it says y is this fraction, and I'm looking for my first derivative. I use my quotient rule. I won't go through the whole thing. So here's quotient rule, simplifies down to this. And now that I have my first derivative, I go ahead and take the derivative again. So here, looking at this fraction, it's another quotient. So I'm going to do quotient rule again. Just making note that when I do the quotient rule, bottom, derivative of top. This time the top is just negative 1. It's a constant, so the derivative of the top is 0. And that simplifies things because that whole part right in here is going to go away. And I have just this. Oops, sorry. Let's see. So I have just this part, and I crossed off the x plus 1 to the first power. So this is a fourth power. One of those can cancel with the numerator, so I have my solution. Okay. Oh, you know what? One more thing. Let me go back. Sorry. When you're looking at the notation here, this one that I've used is probably the most common way to write second derivative. And when you see the 2 here, it's a superscript between the d and y. And when you see the 2 here, it's a superscript after the x. That's actually the correct way to write it. So you have to get the 2's in the right locations there. I have to say f double prime of x is also a pretty common way of saying second derivative. Okay. This one, it asks you find the slope of the tangent line at the point a over 2. So here's the function that they're giving us. Notice there's a's and x's in there. A is supposed to be kind of just a constant, and x is your variable. When I take the derivative, I'm using my quotient rule again. Because a is a constant, when I take the derivative of the top, I get 0. Just like the previous problem, this whole part is going to cancel out. I get to here. And then I have to think, okay, I want the slope specifically when x is a. So I go ahead and plug in a in place of x, and I get this equation. Simplify it down and get your answer. Okay. So here's probably, I guess, one of the most difficult problems that we'll see in this, this section, I guess. They ask you for the equation of the line that goes through this point P that's going to be tangent to the graph of the equation. We've seen find the equation of the line tangent to the graph before, but now we're requiring the tangent line to go through a point that's not on the function. So here we have the point 3, 1. Just to notice real quick, I put here 3, 1 is not on the parabola. If I plug 3 in for x, I don't get 1 for y. Right? 3 squared plus 1 would give me 10. So the point 310 is on my parabola, the point 31 is not. So we're trying to find the equation of the line, or actually there's going to be two lines, that goes through this point and is tangent to our parabola. I'm going to kind of skip ahead to the next slide because I graphed it. So when you're looking at the parabola, this is the black curve here, there's some point 3,1 not on it right here. And notice there's a green line. That should be the easy equation of a line to get because it's horizontal. But you also have this blue line that goes through 3,1 that would be tangent up here somewhere. Okay, so we want to get both those equations. So if you happen to notice that the point given 3,1 has the same y coordinate as the vertex of the parabola, then this green line should be pretty obvious that's horizontal. So you have that equation already, then we just need the blue one. So for equation of a line, I like point slope form. I've plugged in my point as being 3,1. I just need the slope. So how do I get slope? Well, slope is derivative. So for this equation here, if I take its derivative just at any point x, the derivative with power rule is 2x plus 0, or just 2x. That's the slope at any point. And then if I knew the point of tangency, I could plug that in, that x coordinate in, but I don't know the point of tangency. That's why this problem's harder. So what I do is I think of slope as being both the algebra 1 way of doing it, change in y over change in x, and the derivative, the calculus way, derivative. So I have a point 3,1, and then I have some point on the parabola x squared plus 1. And if I go ahead and do my change in y over change in x, just like an Algebra 1 student would do, I have the left side of this equation. And if I take the derivative, as a calculus student would do, I have 2x. These things should be equal because the slope of the curve should equal the slope of the line. And I go ahead and solve this out, the usual. And I got both x is 0 and x is 6. And so those are the x coordinates of the points of tangency when the slope of the curve and the slope of the line are equal. And so we already knew when x equaled 0, that was the point of tangency at the vertex of the parabola. And then we also have now x equals 6. So again, we're looking for the equation of the line, or lines in this case. So m is either 0, right? If I go back to, I just used my slope form, my calculus version of the slope, 2x. If I plug in 0 there, I get a slope of 0. If I plug in 6 there, I get a slope of 12. So my two lines either have a slope of 0 or a slope of 12, and I've got my answers. Like I said, that one was pretty tough. Okay. This one. So when you first look at this problem, it looks like a limit question, and you're thinking, gee, this is 3.3, aren't we done with limits? That was last chapter. Well, the answer is yes. So even though this looks like a limit question, it's actually a derivative question. So if you think back to our formal definition of derivative as the limit of the difference quotient, this fits that format exactly. We have limit as h going to 0. We've got f of x plus h minus f of x all over h. The question is, what is the function f of x? And what value are we plugging in for x? So when you look at this, I can think, okay, well, it must be a 1 that I'm plugging in because usually it's x plus h. And it's raised to the 6th power, so I'm thinking, my initial function must have been x to the 6th. And you can kind of check yourself that you're guessing that the original function was x to the 6th. And if you used this formula, it would be x plus h to the 6th minus x to the 6th all over h. And then when you plug in some number, it should look exactly like this. So, well, I see a 1 plus h. So I'm guessing I plug a 1 in for x. You can check it, like I said, go ahead and use this limit of the difference quotient using this function when x is 1 and see if you get exactly this. So once you realize that f of x is x to the 6th and we're interested in the slope when x is 1, then rather than doing this limit problem, we're going to switch and just take the derivative. So this is 6x to the 5th by power rule. I plug 1 in for x, I get 6. So what this is saying, this fraction, limit of this fraction will equal 6, okay, because this is the definition of derivative. All right, well that was all of the information. I hope that was helpful. There are 3 problems I want you to try, and just go ahead and hit pause, and once you've done that, go ahead and hit play, and I've got the 3 solutions coming up. Okay, so for the first one, find where the derivative is 0. You're going to basically use power rule, term by term, take the derivative, and then you're looking for when the derivative is 0, so you set it equal to 0 and solve. Okay. The second one, find the equation of the line that's tangent to the curve at the point. Well, this time I'm thinking, okay, there was that example where the point was not on the curve, and I know I've done these problems in the past where the point is on the curve, so which one is it? I take 2, I plug it in for x, and I see, do I really get 10? In other words, is this point on my curve? So 2 cubed is 8 times 2, 16, minus 6 is 10. So 210 is in fact on this curve. So this is my point of tangency. So when I'm looking for the equation of the tangent line, here's my slope, my equation of line, point slope formula. So I go ahead and plug in my point of tangency since I know that this point is actually on my curve. All that's left is I need the slope. I go ahead and take the derivative and I plug in the value x equals 2. So I'm looking for the slope of my curve at that specific point. I get 24 and I plug it in and I'm all set. And the last one, the limit again. So when I'm looking at this equation, you should be thinking, this looks like the difference quotient, the definition of derivative. So what is the function that I'm taking the derivative of? So I'm seeing I have a cube root of something, so chances are my function is x to the 1/3 or cube root of x. I'm also plugging in an 8 apparently here because I have, instead of x plus h, I have 8 plus h. So it must be an 8 that I'm plugging in. So this limit is actually our definition of derivative for the function x to the 1/3 and evaluating it when x is 8. So I go ahead and take the derivative of this with power rule and plug 8 in. Probably the hardest part is 8 to the negative 2/3 power. So remember, a negative sign just drops it to the denominator. So you have 8 to the 2/3. You would take the cube root of 8 first and then square it. So cube root of 8 is 2, squared is 4. Remember that 4 is in the denominator. And so I get a 1/4. So a third times a fourth, 1/12. And that's going to do it for today. Thanks, you guys.